Okay. Are there any homework questions? And please state clearly which problem you have a question about.
Dr. Lambers, I have a question. I'm confused on the number 3, what the exact solution is, because I think that I'm doing it wrong.
Okay, and I think, yeah, that one I had not worked out.
Yes.
Okay, so f is equal to 24, and we have u equals, okay, so u of 0 equals u of 1 equals 0, u prime of 0 equals u prime of 1 equals 0, and this is u x x x x is equal to f. So you integrate 4 times. Now integrating, so what will happen is every time, you just keep tacking on a constant of integration.
Yes.
So you'll end up with a 4th degree polynomial. Actually, even though I should say c1 x squared over 2, I'm not going to do that because it's an arbitrary constant. As long as we have the power of x correct. Or I guess if you, one is x to the 4th, it's a general 4th degree monic 4th degree polynomial.
Mm-hmm.
Okay. Well, okay. So, it seems kind of weird to say 24x plus a constant. Let's call it 6c1. Just so it works out nicely like this. Yeah, and now you use this to make sure it satisfies the boundary conditions.
Yes.
Yeah. Well, actually, it's a good thing that I went back and corrected these constants, because now from these 2 you have a derivative.
Yeah.
And can easily see that certain constants must be 0 just to satisfy the boundary conditions at x equals 0.
Yeah.
So which of these constants can you rule out immediately?
I mean C4 and C3.
Yeah. So to make sure that, okay, and then okay, yeah, that's going to make sure that the sum of all the coefficients is equal to 0 in both u and the derivative. So you have a system of 2 linear equations to solve.
Yeah. Yeah, that's what I did. I think maybe my code's wrong then.
Okay.
Because I was getting the same shape. The amplitude was just wrong, like looking kind of wrong.
Oh,
or something.
Okay.
Yeah. So my code's probably just wrong. Okay. Thank you very much.
Okay.
That's exactly what I wanted to know.
All right.
I'm so sorry.
No, once I get the wrong problem in my head, it's so hard to dislodge it. Okay. Any other? Okay. Now, let's see. Continuing with spectral methods. I want to do a quick, here's what we can say at this point. Wow, I really need to just wipe out today. I am so sorry. I should have thought this for a little more. So let's suppose I have u represented by its values as like points, u1, u2, up to un. So each of these, so ui is value of u at a grid point, xi. So we're working with some grid. most of the time we're dealing with uniform grids, but I don't want to I'm not going to insist on at this point. We have some grid of points in our domain, whether it's like 0 to 2 pi for a periodic case or -1 to 1 for the Chebyshev case. The point is, we have the values of u at these points, and we want the value of the derivative at those same points. Now, the reason why what I wrote on the board earlier in erased is not quite what I had in mind as the differentiation matrix is, we don't necessarily have these coefficients ck up front. You have to go get them. But what a differentiation matrix does is given all of the values of u at the grid points, u1, u2 up to un, then we multiply by this matrix dn, and we get a new vector, dnu, which I will call v. So vector v is just that matrix vector product, where vi is an approximation of u prime at the same grid point. So function values in, derivative values out. Now, to highlight the difference between finite difference methods and spectral methods, finite difference differentiation matrices that actually perform this task. Function values go in, and the derivative values come out by a matrix vector product. And here we are making the assumption of a uniform grid. We have matrices like this, like 1 over h, 1's on the super diagonal, and minus 1's on the diagonal. So this is a forward difference. That's only first order accurate. Or center difference. So we have 1's on the super diagonal and minus 1's on the subdiagonal, scaled by 1 over 2h. So this is a center difference. And forward difference, if the accuracy is order h, and the center difference is order h squared. And we could design whatever stencils we want using however many points we want if we want to get higher order accuracy. Spectral methods are simply a way of taking that to the extreme and using as many points as are available to get as much accuracy as possible. So, in a nutshell, what was done yesterday, and now that I have my head on straight, I apologize for any confusion that was caused earlier. Where we represent u I as a sum, uj, here we have the values of u represented as a matrix vector product with itself, where this function is equal to 0, except when the indices are equal, in which case it's 1. In other words, a discrete delta function. And therefore, using this similar logic over there, u prime, so my value bj, this approximation of u prime of xj, is pj prime. So in other words, if we have functions that map function values to themselves, basically it's like an identity matrix, but we view the entries of identity as values of a continuous function evaluated at each of the grid points. I just happen to give you 1 at select points and 0 at all others. Kind of like Lagrange polynomials in a way, in that sense. But here we're not doing polynomial interpolation, we're doing Fourier interpolation. So the whole point of all the crazy manipulations from yesterday was just to compute these. These are the entries that just turned out to be those strange cosine expressions. So -1 for j minus m cotangent j minus m h over 2 for j not equal to m. And when j equals m, it just turn out to be 0. So the thing is, if you can represent u in a manner like this, where you have some set of functions that are equal to 0 at all the grid points, except for one grid point where we're equal to 1, then the derivatives of those functions at all possible differences of grid points gives you a differentiation matrix. What we did yesterday was, the thing is, how you get different spectral differentiation matrices is, how do you represent this function? It's equal to 1 at one grid point and 0 at all the others. What we did yesterday was use trigonometric interpolation, a truncated Fourier series, so that way we could do all these trigonometric manipulations to figure out what these derivatives are supposed to be. But you might choose something else. Like I mentioned earlier, Lagrange polynomials. If you represent functions as linear combinations of Lagrange polynomials and figure out the derivatives of those at whatever points, then you can get a different sort of differentiation matrix, or maybe Chebyshev polynomial, something like that. So that's the idea behind differentiation matrix. Function values go in, derivative values come out, but by using trigonometric interpolation and being willing to use all the function values to compute a derivative at any point, then we can get much more accuracy than those finite difference matrices over there. But one thing I want to focus on today as a immediate follow-up to that, while we're still dealing with periodic problems, is this, that there's one distinct difference between the finite difference matrices over there and this matrix over here. Is, so what we have is most of the entries are non-zero. It's a full matrix. So if you just go ahead and form that matrix and then compute the matrix vector product, if you have n grid points, it's order n squared floating point operations, which is not good, because finite difference, by contrast, those matrices over there, they're very tightly banded, tridiagonal or bidiagonal. So matrix vector multiplication in that case takes order n operations. So you might think, well, why would you do spectral? I mean, yeah, you do get much greater accuracy, but it would be nice if there was a better way to carry out this kind of multiplication than to just forming this matrix and multiplying by it. So there's two steps that I can describe towards a better way. Because if we're already able to represent f as a Fourier series, I wrote this down yesterday. So e to the I k x uk hat. So suppose we already have these coefficients, uk hat. Well, then the derivative is very easy. So Vj, which are, again, I'll stick this notation, is an approximation of u prime at xj, would just be, we could take a derivative of this. What is a derivative of that with respect to x? Derivative of this with respect to x. Yeah. Okay. So in other words, actually, I'm going to write it this way. I'm going to put the ik over here. So in other words, the Fourier series coefficients of a derivative are just the Fourier series coefficients of the original multiplied by ik. Well, multiplied by ik, that'll take no effort at all. That's like order n multiplications. No problem there. So a way of getting a derivative is you have your function values, uj, and you want to go from those to the Fourier series coefficients uk hat for k equals minus n over 2 plus 1 to n over 2. And then you multiply each of those by ik. And then whatever process you use to go from the original function values in your grid points to the Fourier series coefficients, you reverse that process to get your values Vj, which are your derivative approximate derivative values from 1 to n. So you think, okay, if I could just do each of these stages quickly, then that's an efficient way of getting a derivative. But what about these three stages? Well, this one, from here to here, that's quick. You're just multiplying each value by ik, so that's only order n operations. But what about these? Well, if we want to use this formula, like we have these coefficients already, and then we want to carry out this sum for each of the grid points, each j, from 1 to n. Well, that's n summations. Each summation takes order n operations because there's n terms in here. So that's order n squared. So that's not good. Also, to get from here to here, I wrote that formula on the board yesterday. uk hat is a sum, h, which is equal to 2 pi over n, times the sum of e to the minus ik xj uj. So again, we have to compute n of those, and each one takes order n operations. So that again is order n squared, using the definitions that we have. So we're no better off than what we have here, this differentiation matrix. But if we can find a way to perform these operations more rapidly, then we would have an efficient and still much more accurate differentiation process than something that is now a reasonable alternative to finite difference. So that's what I'm going to show you now is how we can make these things faster. And at first I was thinking, like, oh yeah, I could just whip that up. I remember how it goes. I've done it before. But I don't trust myself today. So I printed out the notes. Well, this is actually not from the notes. This is from a textbook. Well, our textbook. So I can make sure that it's done right. Okay. Make sure I was getting all that. Okay. And the way we're going to do this is by trickery. I just have to adapt the notation on this page to the notation I've been using. So, all right. So the formula I had before, UK hat is the sum of minus I k x j u j. All right. One thing I'm going to do though, I'm going to change notation just a little bit so that I don't screw this up. By going, instead of from 1 to n, I'm going to go from 0 to n minus 1, but I'm going to keep the same definition of xj. Xj is going to be j times h, which is j times 2 pi over n. But can anyone tell me why? So what I did was I changed the formula to use it from using these points, x1 to xn, but not using x0 up to xn minus 1. Why is that okay? How come I didn't actually change anything, like the value? What kind of functions u are we dealing with?
Are we doing periodic?
Yes, it's periodic.
Oh.
Yeah, so u0 equals u then. X0 and xn differ by 2 pi. Careful, we're not expecting the exponential. Okay, so then again, this is insurance against screwing up. The notation on this page is very different from what I've been using, so we're still at risk of screwing up. But okay, now I'm going to fill in what xj is. All right, so I have e to the minus 2 pi I j k over n times uj. So alphabet soup in there. Okay, the next thing I'm going to do is I'm going to break this sum up into two. And I'm going to assume, as I have been assuming, that n is even. So I'm going to break this up into a sum where one sum deals with the even numbered values. So even numbered grid points, 0, so u0, u2, u4, u6, etc. And then the other sum will deal with the odd ones. So that's going to give me e to the minus 2 pi I. So here we have the even indices for grid points. So u2j. And then another sum for the odd number points. So that's going to be e to the minus 2 pi I, and then I'll have 2j plus 1 over n. u 2j plus 1. All right. Now, I'm going to rewrite these as the minus 2 pi I j. So instead of multiplying by 2, I'm going to divide by 1/2. So this will be n over 2 down below. U2j. And I'll do the similar thing in the other one, but I have this factor here. If I were to break this up, this would be just the exponent, minus 2 pi I 2j over n, which is exactly the same as over here. I can rewrite it this way. But the other part is minus 2 pi I over n. So what's helpful here is this part of the exponent does not depend on j at all. So I could pull it out of the sum. So I'm going to have e to the minus 2 pi I over n. And then I'll rewrite the rest of the exponent in the same way as before. Now, so I can condense this now to in the notes I have a scaling factor, but here I have no scaling factor. Okay, but not going to worry about it. So this would be I don't really have any convenient notation to express this, but this is something's missing here too. Oh, I dropped the k along the way. There needs to be a k in each of these. Okay, there's something that's missing. Okay, so if you compare this sum to this one, this is a really it's like a discrete Fourier transform. Using n points of u, and we're just picking off frequency k. And u, we have n values of u, so we do an n-point discrete Fourier transform. This is an n over 2 point discrete Fourier transform. Because you replace n with n over 2 throughout this, you get exactly this. It's just that here we have all the values of u, here we only have half of them, the even half. So this is...
Are you talking about the fast?
Yes.
Yeah, fast Fourier transform?
Yes.
Split it even? Okay.
Yeah. Was that covered in one of the other classes you took? I don't remember.
We covered it in 773.
Oh, okay, yeah.
Yeah.
All right. Yeah. So this discrete Fourier transform of size n over 2 of u sub e, which I'll call u even, choosing frequency k. And then we have this, these are called like twiddle factors, e to the minus 2 pi I over n times another discrete transform of size n over 2 on the odd numbered points, choosing frequency k. Now, here we have k going from minus n over 2 plus 1 to n over 2. These will only be defined for minus n over 4 plus 1 to n over 4. but then you can take advantage of like some periodicity to make it work for any of the values of k. The point is, when you have a problem, if and we use t to refer to time, like running time, like complexity. If the running time for a problem size n can be expressed as solving two problems of size n over 2, so in other words, a n-point discrete transform is broken down into two transforms of half the size, and then it takes only order n operations to patch those solutions together to get the new solution. So once I have these, it only takes order n operations cleanup to assemble the solution of the original problem from the two solutions of the problems of half size. Then, so this is a general recurrence relation. When this happens in general, the overall running time is on the order of n natural log to base, or it's not natural log to base 2 of n. So this is the idea behind the fast Fourier transform. To compute these coefficients as rapidly as possible. So instead of order n squared operations using the definition way over there, it takes order n log n. So to give you an idea, let's suppose that n is 1,000. So order n squared, that would be 1,000,000 operations. But log to base 2 of 1,000 is roughly 10. So now you're talking 10,000 versus 1,000,000. You sped it up by a factor of 100. That difference would only grow if n gets even larger. So it makes a huge difference in the running time. That's why BFFT is one of the top 10 algorithms of the 20th century. You could go the other way, like for the inverse fast Fourier transform, to go from UK hat back to UJ. So the two stages identified over there that are too slow, getting the Fourier series coefficients and then going back to the values in what we call physical space, instead of order n squared time, they both can be done in n log n time. So, and this implicitly carries out the same operation as if you use that differentiation matrix. So spectral differentiation, so that spectral accuracy we like to have, can be done in order n log n time. So that's why DFFT is so great. Well, FFT is used for many things, but it's what makes spectral methods practical for these periodic cases. So any questions about this decomposition to get for FFT? Okay, so nothing to it. All right. Yeah, because I want to complete that as far as like, okay, we have this differentiation matrix that gives us so much accuracy, but if it's so much more expensive to use, then why use it? And the same idea can be used for second derivatives, like instead of multiplying by ik, you're multiplying by the quantity ik squared, or in other words, minus k squared, for second derivatives. Now, but having some idea, if you want to express this differentiation operation, right now is now a three-stage process. FFT multiplied by IK, inverse FFT. But if you want to describe all those operations put together as one matrix vector product, so what I did yesterday to come up with that strange matrix that has all the cotangents, that is the matrix that does that job. So it's still good to know those entries, at least from an analytical standpoint. And also, the formulas have been worked out, for instance, for a second derivative where you get cosecants, and those are given in the notes. So I'm going to step through an example of how the FFT can be used to efficiently solve this kind of PDE. we have Poisson's equation in 2 dimensions. On domain omega, which is square of size, side length 2 pi. And we'll assume that u is 2 pi periodic in both variables, x and y. So periodic boundary conditions all the way around. We can write f of x, y. I swear I need eyes in the back of my head. Okay, so it's going to cut off. Writing out f as a Fourier series, Fourier series coefficients have 2 indices because we're in 2D, and these are Fourier basis functions. So you take really it's products of one-dimensional Fourier basis functions, e to the I kx, e to the I ly, for all possible combinations of k and l. And what you can do is you can get these coefficients using the FFT, fast Fourier transform. So all that's been generalized to whatever number of dimensions that you have, and you get the efficiency that you see in the one-dimensional case. Okay, and so in Matlab, there's FFT and IFFT for fast Fourier transform and inverse fast Fourier transform. In 2 dimensions, there's FFT2 and IFFT2, and there's also FFTN and IFFTN for general n-dimensional transforms. So you need to do that to get a hold of these coefficients. So then what you do is you take the Laplacian, so you assume that U has a similar representation where your coefficients UK hat multiplied by these same basis functions. If I take the Laplacian of this, that means I'm differentiating twice with respect to x, which multiplies by ik squared. And I'm also differentiating twice with respect to y, which multiplies by il squared. And those are added together. So the Fourier coefficients of a Laplacian would be Fourier coefficients of u times, well, it's minus Laplacian. So I have k squared plus l squared. So what we have here is minus ik squared plus il squared. This reduces to this. Okay. Now we have minus Laplacian of u is supposed to equal f. So all I have to do now is equate these to each other. And that means I equate these coefficients. And now I can just solve easily for the Fourier series coefficients of u. It's Fourier series coefficients of f over k squared plus l squared, as long as KL, that ordered pair, is not equal to 0, 0. So all I have to do is take a 2-dimensional FFT of f to get these coefficients. Go ahead and divide them all by k squared plus l squared. Then I do a inverse FFT to get u at points xi, yj. So the whole process takes order n log n operations, where n is the number of, n is the total number of grid points. So in both x and y together. So if you have n points per dimension, it's order n squared log n squared. But remember, log of n squared is just 2 log n. So that works out pretty nicely. So you don't suffer as much from like a cursive dimensionality. So one thing that's essential, though, if it comes out of this, is we must have f(0, 0), that f hat 0, 0, must be 0 for a solution to exist. Because otherwise we just don't have any way of getting that coefficient. Now, well, first, any questions about the solution process before I talk about that more? Now, what's the whole problem with f(0, 0)? Because f hat 0, 0 will be multiplied by this function with k and l both equal to 0. But that's just 1. In other words, it's the constant term. Now, if you can imagine a function whose Laplacian is equal to a constant, so what sort of function would have a Laplacian that's equal to a constant? Well, I'll give you an example. A function like x squared, or x squared plus y squared, because if you take Laplacian of x squared, what's the Laplacian of x squared?
2.
Yes, because you just take uxx. Or if it was x squared plus y squared, the Laplacian would be 4. The point is, a function whose Laplacian is a constant must itself be equal to some sort of quadratic function, generally. Those functions, good luck getting those to be periodic. So that's why we have this situation here. It's kind of similar to what happens in the Neumann boundary condition case, where you have this compatibility condition to be satisfied. Now, on the other hand, so let's suppose this condition is satisfied. Now a solution exists. But the solution is not unique. Can anyone think of why? What would be a way to vary the solution? You're roped into this. You have to do this. Any solution satisfies that. But what flexibility do you now have in a solution?
Since it is periodic, so we have that shift. That's why it's not unique, right?
Getting error. You could choose u hat 0, 0 to be whatever you want. So all solutions differ by a constant, which is also the same thing I think happens in the Neumann case. Because the Laplacian of a constant is 0. So, yeah, so you need some extra condition to specify that, or you can just choose whatever. Like it's very common, for instance, to choose the solution of 0 mean. So u hat 0, 0 would just be 0. Okay. All right. So sophisticated idea is how you can use spectral methods in the periodic case to quickly solve PE. Now here I've assumed that k and l can be anything, like go from -infinity to infinity. But in a practical setting, you have to cut off the Fourier series at some point. So what happens is you get a spectrally accurate approximation to the solution, because you are band limiting f to a certain range of frequencies, and then for that f, you're actually solving Poisson's equation exactly. And certainly the more grid points you have, the more accurate your solution will be. But you get spectral accuracy, not of this order h squared or h to the 4th accuracy, it's spectral, so error goes to 0 faster than any power of h, as long as the function f is smooth. So that's important, because solutions of so that means the solution too will be infinitely smooth. Okay, so that's periodic. So then after a break, I'll start talking about non-periodic. All right, cut off again. So these are formulas for the entries of a differentiation matrix. For the off-diagonal entries and then the diagonal entries, whereas a shorthand, we just have these products of differences of the Lagrange points. It's not easy to show. I actually saw this in a book by Trefethen, Spectral Methods Using Matlab. he gives an exercise to show that these formulas are true. It's not that bad, but it is kind of tedious. What is a bit more nightmarish is, the thing is, this is true for any choice of your interpolation points. This is not restricted to Chebyshev points. So, so in fact, everything I wrote on this board here, this is how you turn to differentiation matrix. If you are approximating on an n+1 point grid by a polynomial of degree n, and you want a differentiation matrix, this is how you do it. Now, if we specialize this to the Chebyshev points for xj, then we have more specific formulas for this. And it's kind of a nightmare. It's really a nightmare to show. I actually also given as an exercise in Trefet's book. I think one of the most dastardly exercises of all time. I played around with it, and if you use trig identities, you can see how these things work out, but I have better things to do. So, the diagonal entries are strangely not zero. You'd think they would be, like it would in the Fourier case, or finite difference, but they're not. So it's minus xj over 2, 1 minus xj squared for most diagonal entries. But the very first entry is 2n squared plus 1 over 6, and the bottom right entry is minus that. The other off-diagonal interior entries all have this form, minus 1 to the I plus j over xi minus xj. Now, in fact, this xi minus xj denominator, you have that up here. But what's interesting is this ratio, ai to aj, turns out to be minus 1 to the I plus j. Really a pain to prove. Don't bother. Unless you really have a lot of time in your hands. But yeah, it takes the trig identities like I used yesterday. And then for the rest of the matrix, they go to the boundaries. You actually have to use, like, well, actually, I think there's like a L'Hopital's rule to show some of these. Okay. Actually, no, I'm thinking of something else, sorry. That's also dastardly to show. So like right now I'm writing the entries in the last column. It starts at this entry. Generally they have this form until the very last one's equal to this. But it has similar formulas elsewhere. The matrix is, except for the diagonal, the matrix is skew symmetric as differentiation matrices typically are. Now, if I were to try to construct this matrix in Matlab, probably what I would do, because I feel like the most straightforward way to program it, is here you'd have like these if statements, all these special cases, and so forth. But what you could always do is, if you keep in mind that these entries are all derivatives of Lagrange polynomials evaluated at certain points. Well, you could form Lagrange polynomials using Matlab's polynomial functions, using, like for instance, polyfit, where you have your x values and your y values are columns of identity because they're all equal to 0 except one entry is equal to 1. And then you can use polydir to compute the derivative of Lagrange polynomial, and then you can use polyval to plug in a grid point. So using Matlab functions like polyfit, polydir, polyval, you can construct a differentiation matrix not just for Chebyshev case, but for any selection of the xj. Okay. So here's for first derivative, and then if you were to square it, you would get the spectrally accurate differentiation matrix for the second derivative, and so on. So that's one way to carry out Chebyshev differentiation, but just like in the periodic case, this is a full matrix. So again, order n squared operations to compute a product, which you don't want to do. And I have just enough time to explain an alternative that, believe it or not, uses the FFT. So even though it's not periodic, and really this one requires a nicer group points like a Chebyshev points, that the FFT can still be helpful. And the reason why it's helpful is how the Chebyshev points are defined. Chebyshev points, I'll leave this formula up here, they're cosines of angles that are equally spaced. So a nice pictorial way to understand the Chebyshev points is if I draw top half of a unit circle, however badly, and I choose equally spaced angles as I go around the circle. So this is like my pi j over n. And then I take the cosine of that. But the cosine of a point on the circle is the what? X coordinate. So I just take the x coordinate. So I drop a vertical down to the x-axis. And the resulting x values are Chebyshev points. And that has the natural effect of being clustered closer together. It's easier to see when you have more points at the boundaries, and they're spread further apart in the interior. But the fact that they're equally spaced in terms of their angle is what lets you use, I should go to the computer. Dang it. Okay, so, visual depiction of Chebyshev points. Okay. So, here's how you can perform Chebyshev differentiation via FFT. So what you do is first you perform what's called an even extension of your u values. So I define a new vector. In the notes it's uppercase U. So I'll make my u those nice and big. So you have your points u1, u0, u1, u2 up to un, and then you reflect, because what you're doing is here's your function, it's not periodic, and you reflect it across a vertical line. So then you have un minus 1, un minus 2, all the way back down to u0. This, with respect to this line, is an even function. That's why we call it an even extension. Okay, so now we perform an FFT on that. So that'll take order n log n operations. So UK hat is, now before we had our spacing h, which was 2 pi over n. But now we have pi over n. We have twice as many points, therefore half the spacing. So you think this is h over 2. And the thing is, since we're working with theta equals pi j over n, and now we have 2n points. So actually, you can think of this if you want as 2 pi over 2n. E to the minus ik theta j uj. So, and theta j are the angles, which are equally spaced. So it's like we were gone into like circular space to do an FFT because for the equal spacing. And this is for k equals, instead of minus n over 2 plus 1 to n over 2, it's minus n plus 1 to n, because we have twice as many points. Basically, if you take the old formula for FFT from before, just replace n over 2 with n, and you get this. Okay, now you differentiate. Okay, so this is the second step. Third step, you carry out the derivative in frequency space by multiplying by ik, like before. And then, which would mean that that coefficient, that corresponds to the constant term, so that would be 0. Of course, that's a natural consequence of this. Wait, my lines are getting jumbled up here. Okay. Oh, well, happens is we have this coefficient left over in a way. So we just set that one to be 0. Okay. All right. Then we compute the inverse FFT to get ourselves back into at least circular space. So 1 over 2 pi. So this is the same inverse FFT formula, just with using twice as many points. Okay. Oh, and I need a name for this. I'll call that WJ. So what we've done here, though, is we've taken the derivative not with respect to x, which is what we want, it's with respect to theta. So in order to fix this, we now need to basically undo the even extension. So little wj, which is our approximation of u prime at xj, is defined to be minus capital Wj over the square root of 1 minus xj squared. And that might seem rather strange, but you can think of this as du d theta dx, evaluated at xj. Now, what is theta? Keep in mind, theta is pi j over n. But you can also think of theta as inverse cosine of x. So because what is xj? It's cosine of pi j over n. It's cosine of theta j. Well, the derivative of inverse cosine is minus 1 over square root of 1 minus x squared. So that's what we're doing. It's just chain rule. Let's make clear, that's a minus and a fraction, not a long fraction bar. Okay, and now you're pretty much done. The only thing that is remains is your Chebyshev points include the boundary points, minus 1 and 1. So this doesn't work for the boundary. So this only holds for j equals 1, 2, up to n minus 1. Your interior points, you can just do this, and it's fine. So what I'll wrap up with is how you would handle the boundary points. And unfortunately, this is not explained as well as I would like, because based on the notes from the MIT site, which were then taken from Trefethen's text, but there's a notation mistake in Trefethen's text that I could not fully unwind. I should maybe tell him that at the next time I see him in a SciEM meeting. Or maybe he's posted corrections, I don't know. That there's these formulas for values at the endpoints. You basically get by working with this and applying L'Hopital's rule. And what you get is something pretty strange. 1 over 2 pi. Okay. I need to fix my notes as well, but oh, no, my notes are fine. I just need to give another definition. So a bit of notation to define, and I'll do that, and then it'll be done. Okay. Now, the AN are the coefficients of, okay. So we have the AN are the coefficients of this function in a cosine basis. But what is this function p of theta? P of theta is our interpolant of a function capital U of theta, which is our original function u evaluated at cosine theta. So in other words, you take your function you're trying to differentiate, you think it's a function of cosine theta, you make it a function of theta rather than x, and then you interpolate that, but it's a trigonometric interpolant, using a Fourier cosine series. And you could use just a cosine, not sine, because you perform an even extension, and cosine is an even function. So all the sine terms, if it were here, would be 0. Okay. And I can actually express this in terms of the Fourier coefficients computed over there. VBI k theta VK hat. Wait. Okay. Well, these would relate to these. The trouble is in Trefethen's text, he has a capital VK hat, but he's a small VK hat. Elsewhere it's not defined, and I couldn't make sense of it. The only other piece of notation to define is I have this sum with a prime here. That's an interesting notational convention I've not used in class before. That the sum of a list of values with a prime, instead of just adding them all up, what you have is you actually multiply the first and last values by 1/2. So this is a common convention to use, especially with periodic functions, to do something like this. So those are the formulas for the boundary values of your derivative in terms of the coefficients of your function in a well, in fact, you could think of this as, this is also same as a Chebyshev polynomial, Tn of x, where x is equal to cosine theta. So, in other words, if you expressed your function u as a linear combination of Chebyshev polynomials, these coefficients are what you would use up here. All right. So the main point I want to make of this is we use an FFT multiplied by IK to the inverse FFT, and then cleaning everything up after that only took order n operations. So the whole procedure is order n log n floating point operations compared to the n squared if we used the matrix that I wrote out before. So whether it's periodic or not periodic, you could do spectrally accurate differentiation over n log n operations using an FFT. So working with a regular Fourier series for periodic case, Chebyshev points for the non-periodic case. Okay, so I'll do some examples of how we use these to solve PDEs tomorrow.